diffraction gratings. This is section 33.3. One of my, honestly, most fun topics. And it's pretty amazing what you can do with diffraction gratings. Diffraction gratings aren't just double slits. With the diffraction grating, it's like mini scratches really close together. Okay? You can take a razor and make a couple slits there to get a double slit. You can take one slit on the laser and shine a laser through it. That'll give you a double slit. That works. I've actually used some of that concepts before on some of my test instrumentation I've made. But if you can make what's called the term is a ruling engine, R-U-L-I-N-G, and it basically it makes the equal distance slits on a ruler. Those little marks, those tick marks you call them, and how fine you could make that became something of a contest, as you could almost say, by engineers in the late 1800s. How close they could make those together and how fine, evenly spaced they could. One of the things you can do, though, if you shine light on these mini spacings, be really close together, you'll get a pattern that's much more evident showing diffraction than the Young's double slit experiment. And you can make an argument that those guys were the first real precision engineers. Not modern ones, but modern precision mechanical engineers. They really pushed the limits of mechanical precision as you can get. Of course, me having a PhD in mechanical engineering with a precision engineering concentration, I find that stuff, how precise you can make mechanical scratches apart from each other, pretty darn interesting. The gearing and all that works. It's pretty darn cool. It's way better than I am mechanically, but how they did it was pretty interesting. So let's think now of, rather than just a double slit, lots of slits. So when light is incident on this, each one acts as a little emitter. You can keep on going, and they each one go out as an emitter. Each one go out. Now, in this case, what we're going to do, we're going to say D in this case is the distance. Here is D. Distance between each slit. If you can make this distance fairly close to the wavelength of light, you can really get light to spread things apart and get those orders first, and the other orders, of course, separated a whole lot. Okay? So let's have a view screen out here. Okay, of course, the distance from here to here, we call that L. From the diffraction grating, something like this. Ooh, and you think a CD acts as a diffraction grating. If you had a little laser pointer and a CD, you can see diffraction grating effects that way. I didn't bring one in today, but you can see that really easily. A lot of times they're kind of rainbow patterns sometimes. You'll see that. If you ever see those flat lenses, flat pieces of plastic, Fresnel lenses they're called sometimes, you can see like a rainbow pattern on it. That rainbow pattern you're seeing is diffraction. Just at different wavelengths, it's diffracting it differently. You shine a laser on those and you can see it. Alright, so that's that. Let's see. And what you'll see is a very prominent and a very in the middle of it, you'll see a real and I'm going to do the intensity out here. And you'll see a real prominent first 0th order turn. Then the intensity will go up a little bit, a lot less than this one. This, of course, is my favorite one. The first then a second one, and you may see a third order from that. Depends on the wavelength, the slit spacing, the geometry of the situation, how close or far away you are, how big your view screen is, how wide your view screen is, of course. All right? And of course, it's symmetric on the other side. All right. So that's the intensity you would get. So further away, you see this now. What happens is, our eyes don't see this real good. We'll see a big spot in the middle, and then we'll see a few other little spots. That's what we tend to see here. And what I'll tell you is, if you can make these nice and close together, what happens to this width? Well, you can compress the width of the first order as d, the gap distance, approaches the wavelength of the light. When it gets really small there. When it gets really, really small. Okay? Let's see here. All right. So let's look at some of the positions of it. So I'm going to look at some positions. And the equation you'll see used a lot, basically, that governs diffraction gratings. And that is N lambda equals D sine theta. So you're like, what the heck is sine theta? Well, let's think from this position, this is going to be the first order, second order. This is your theta. D is here. N is your order number. You do takeout, right? Oh, everybody's doing takeout now. It's your order number, your first order, second order, whatever. And one of the things I will say I didn't really hit at too much is, with diffraction gratings, lots of times these peaks can be very similar in height. Depends on how close you get them, of course. But you can get them so that the peaks are fairly similar in intensity that way. And actually messing around with diffraction gratings, spacing and stuff, you can really engineer. I mean, holograms are basically very, very fancy diffraction gratings, if you want to think of it in many ways. And that change in 2 dimensions, not just a bunch of scratches in a straight line, they're fancy dancy scratches, you could say. All in all sorts of forms and figures. So that's the basic equation you're going to use. And the position of it, how far away this is, this y value, this would be y to the first, of course, but yn, or n, equals the length times the tangent of theta, where m is the bright fringe order. Okay. Now you might be saying, well, there's an m there, and actually I did d. Let me call this m. Let me use this m. Oops, I hit the chair. You didn't see that because it's off screen. This order number and this order number work, they're basically the same. They're basically the same, is what I was going to say. Okay. Notice there is a wavelength dependency here. Because what you end up doing, the way to solve these problems, I'll tell you is use m lambda equals d sine theta to determine theta, and then use theta to get the position of that fringe. So this helps you predict the fringe, or back out the other way, start at the position of the fringe, figure out what your theta is, and find either the wavelength or the slit spacing on that diffraction grating, how close those lines on that grating are. That's where you're going to use problems. These are two-step problems, okay? Do know that these are two-step problems when you do these. Now, it can be transmissive, lines going through something clear like this. I don't know if you see a rainbow pattern. The rainbow flavors. No. So you might see a rainbow here a little bit. This is a transmissive grating. A CD would be a reflection grating. So it's a reflection grating. It's like mountains and valleys, as opposed to scratches, which like in a piece of plastic film. Mountains and valleys basically form that. And of course on a CD, those are circularly symmetric as they go out for that. So let me show you how this works. We'll use the green laser again. Green laser. I am going to get the lights. You don't see much light difference change because it automatically kind of adjusts. But I do. So I'm going to set this here. Woo! My goodness, do you see that? Maybe you don't. Let me turn it this way. And what's interesting with this is, now I can see off screen there's two orders. You see the first one's real bright. You got a second order. First order is less bright than the second order. Let me see if I can throw that off to the side there. The second order is not as bright. Now the book makes it look like all the orders are the same brightness. That's one thing that bothered me, the way the book presents it. The orders are not going to be the same level of brightness. Okay, now you can engineer that if you want in the way you do your grading spacing, but the work I did when I was at a company called Digital Optics, we did we could put diffraction orders wherever the heck we wanted to, based on how we did our pattern of scratches that in our case, we used techniques to use to make computer chip technology to make scratches. But that's a sidebar. But if you see out there that second order way over there, right there, you see it, it's not going to be as bright as the first or the first one. Okay? But that's the spacing here. Now, if you have a diffraction grating with the spacings not as close together, those fringes actually get closer together on that. Those fringes get closer together. And of course, that comes out of the equation. If you look at D, when D gets really, really small, you could show that Y, if you solve that equation for Y and backed it out, Y would get really big when D gets small. So those are inversely related functions there. You could set one equation up, but it's not really worth it. Okay. Now that's with here. Now I'm going to rotate it 90 degrees, and you notice here, now you've got vertical. What's happening? Remember we talked about how the lines are. It basically, if the lines are vertical in this case, it's going to spread everything out horizontal. When I rotate, and you hear me rotating it. When you take the grating, rotate it 90 degrees, now the lines, the scratches are horizontal, but it displaces everything in the vertical direction there. And that's just a property of how light does. You can explain it using something called Fourier analysis. That's math you probably haven't even heard of. It's really cool and I like it, but it's junior, senior, minimum level stuff. Okay? Diffraction gratings are nice. Play around with the laser pointer with the CD at your house. Notice it doesn't depend on how far away you are. What matters is, now if I put this really close, you guys can see the orders. And yeah, you can barely, let me try it this way. Now you can see a third. It was being blocked or obscured by the case this is in. You can almost, I can see a third one there, barely. Okay. If I rotate it 90 degrees, you see how that works. Okay, if I change of course the length, it's got less throw for it to spread apart. And that's why it does that. It's really cool stuff. There's lots of applications of diffraction here. Feathers, iridescence in feathers is a diffraction effect. Different colors of light. Now notice the gap here. Let me do it with the red laser. Oops, that's my green one. It's really weak. I initially had it up today. It's not as much. It's not as much. There versus there. It's different. It's different as a function of, actually it's greater with the red. Yeah, it is greater with the red. My apologies. It's greater with the red. There we go. Looks like maybe it's a tad greater with the red. I think I said earlier, as the wavelength increases, then it would get closer. Actually, it's the opposite way around. That was my mistake from earlier. Okay. There's an energy perspective in there I didn't take into account that I should have. I should have known that, but it's okay. I make a mistake. Once in a while, I'll make a mistake. Kelsey, I'll promise not to let it happen again as best I can for the rest of the semester. All right. That's diffraction.